get good marks at the semester end. If you are unable to share your screen, or if you are unable to give answers, if you are not giving response through chat box or through mic, I will understand that you are not active in the lab session. Okay, so you have to lose your marks. Go through this theory for 5 minutes. Section 1, roll number 19.
Yes, sir.
What is the full form of RTD?
Sir, could you repeat the question? Sir, I'm having bad internet.
Full form of RTD.
Sir, resistance temperature detectors.
What is the use of RTD?
Sir, it is used to measure temperatures.
Okay, 19. Section 315.
Yes, sir.
Can you share your screen?
Okay, sir.
Can you scroll up? Right. Wow. What is the formula for R?
IL by A, sir. Resistivity. Resistivity rho L by A.
What is rho?
Resistivity
Rho
of
is
the metal.
resistivity. L is?
Length of the metal.
A is?
Area of cross section.
Right. So if you increase length, what is the effect on resistance?
It also increases, sir. It is directly
Right.
proportional.
If you increase cross-sectional area, then?
Inversely proportional, sir. It decreases.
Right. Stop sharing. CSC 5, roll number 1.
Yes, sir.
Can you share your screen?
Yes, sir.
Scroll down. Yeah. What are the different materials we use in RTD?
Sir, platinum, copper, nickel, tungsten, balco.
Which is the most accurate material?
Platinum, sir.
Okay. What is the full form of RTD?
Resistance temperature detector.
Right. Okay. Roll number 1. CSC 737.
Yes, sir.
Share your screen.
Yes, sir.
Right. Scroll down. Show me the formula for RT. Above the graph, yes. Read out that formula, roll number 37.
RT is equal to R naught into 1 plus alpha T minus T naught.
What is RT?
Resistance of temperature at temperature.
Read once again.
Resistance at temperature T.
Resistance at temperature T. What is R naught?
Resistance at reference temperature.
Right. What is alpha? That is not A. It is alpha.
Alpha.
But it is looking like A. Okay. It is appearing like A.
Yes, sir.
What is alpha?
Temperature coefficient of resistance.
Okay. 1 minute, students. Yeah, sorry, 37. Right. So what is alpha?
Temperature coefficient of resistance.
Right. What did you understand about this temperature coefficient of resistance?
Sir?
See, if you have platinum,
Yes, sir.
if you have copper,
Yes, sir.
if both metals, why are you scrolling down? Okay, right. Here we have temperature coefficient.
Yes, sir.
Yeah. So 37,
Yes, sir.
if you have 10 centimeters copper metal rod
Yes.
and 10 centimeters platinum metal rod, and if you keep those two metals at 100 degrees Celsius, okay,
Yes, yes, sir.
before placing at 100 degrees Celsius, it has some resistance. Copper and platinum both are different.
Yes, sir.
Let us say copper resistance is X and platinum resistance is Y. And after placing at 100 degrees Celsius, X will not be X, Y will not be Y. Did you understand
Yes.
that?
Yes, sir.
But the next value of X and next value of Y, depending on temperature coefficient of metal, that is the copper temperature coefficient and platinum temperature coefficient, their resistance will increase in different ways. Here graph shows that.
Yes, sir.
Okay, so green color shows platinum,
Platinum.
red color shows copper, and light blue color shows nickel.
Yes, sir.
Platinum resistance is increasing linearly, and they are copper and nickel also increasing linearly,
Sir?
but they are not.
Sir, can you repeat it?
Yes. Hello.
Yes, yes, sir.
Yes. Platinum is increasing linearly, but copper and nickel are not increasing linearly. They have some different shape. Okay. So most of
Yes.
the cases we use platinum in RTD.
Yes, sir.
So temperature resistance coefficient. Okay. Scroll down.
We have nothing, sir. This is the last one.
Okay, right. Scroll. Show me the formula. Right. So temperature coefficient of resistance is different for copper, different for
Platinum.
platinum, and different for copper. Okay.
Yes, sir.
Right. Stop sharing. Now, students, click on aim. Click on aim. So today's experiment aim is to understand the working principle of RTD. And here we have two parts. First one is analyzing the static characteristics, and second one is dynamic characteristics. With these two, we will understand the RTD performance. Here we have to study static characteristics and dynamic characteristics of the RTD. With that, we will see the performance of RTD and how different parameters are affecting the performance of RTD. This is our aim. Now, click on procedure. Okay, click on procedure. Students, I am giving you 5 minutes time. You go through this procedure. These are the steps we will perform in the experiment. So go through here you can see experiment 1 and experiment 2. These are the first part and second part. Okay. So in this website, they are representing as experiment 1, experiment 2, but both comes under the same experiment. First part is analyzing the static characteristics. Second part is analyzing the dynamic characteristics. Okay. So go through this procedure. I will give you 5 minutes time. Then we will move to the conduction of the. Now students, click on the audio video. So here we have the details of the procedure in video format. So watch this video before doing the experiment. Watch this video before doing the experiment. This is a 5-minute video. So go through this video. Students, now right click on simulator. Right click on simulator and open the simulator in a new tab. Right click on simulator, open simulator in a new tab. And this is the simulator tab. Again, here we have to click for simulator. And here we have to conduct our experiment. First of all, we have to select material, platinum. If you select the platinum, and we will get data, alpha value and temperature range. And what is the temperature range? Here we are seeing -200 to 850. So if you are using platinum RTD, you can use that platinum RTD within this temperature range from -200 degrees Celsius to 850 degrees Celsius. So this is the meaning of the temperature range. Now we have to select R0. R0 is the resistance at 0 degrees Celsius. So if you are selecting 100 ohms for platinum, you can choose. Or if you want to 200, if you want to 300, if you want to 500, whatever value you want, you can put as R0. So select R0, students. After selecting R0, you have to click on get temperature. So this website is assigning 471 degrees Celsius to me. If you click on get temperature, you will get different temperature values. My temperature value here, what you are seeing is different from your website value. Randomly, it will give temperature value. So what is the meaning of this experiment? If you are using platinum RTD, if its alpha value is this much and R0 value is 100 ohms, find out the RTD resistance at 471 degrees Celsius. Find out the RT, find out the RTD resistance. RT means resistance at 471 degrees Celsius. So find out the RT at 471 degrees Celsius. How to calculate RT at 471 degrees Celsius? Here we have link for formula. If you click on formula, you can see this. Students, are you able to see this separate page, formula page?
Yes, yes, sir.
Right. So here we have the formula for RT. RT is equal to R0 into 1 plus, here I cap. This I cap is nothing but alpha. Plus or minus I cap into T. What is T? Go to the theory. If you go to the theory, we'll get formula. See, RT is equal to R0 into 1 plus alpha T minus T0. So this is the formula. Here you have to substitute those values. If you enter correct RT value, then you have to submit. After substituting 3 values, after finding out the 3 RT values, you can plot graph for this first experiment, first part of the experiment. Okay. Now randomly I will call roll numbers. I am giving you 5 minutes time. Those students has to share their screens to show graphs and their RT values. Roll number 1 in section 9.
Yes, sir.
Can you share your screen? So how many values you have verified? Roll number 1.
One value, sir.
Yeah, click on get temperature once again. Right. Now calculate for this minus 116 temperature RT value.
Sir, we need to calculate three values, no, sir?
Yes.
Yes, sir.
Then you can go to the level 2.
Yes, sir. By plotting the graph, we got a straight line.
Yes, correct.
Yes, sir.
If you do conduct the experiment for 3 different values, you will get a you won't get straight line. You will get a different shape of the line, different shapes for the line. Wait. Roll number 1. Again, you have to click on get temperature. Calculate for this, then submit, then you can plot. Okay. Roll number 1.
Okay, sir.
Right. Stop sharing. CS 11. Roll number 20. CS 11. Roll number 20. If you have problem with mic, you can give response through chat box. Roll number 20, CS 11. Roll number 20, I'm giving you 5 minutes time. Within these 5 minutes, you have to give response. Okay. Otherwise, I will remove from the session. Roll number 44, CS 11.
Yes, sir.
Can you share your screen?
Sir, can you give me 5 minutes, sir? I'll do one share.
Okay, right. CSC 1149. CSC 1149. Right. Do the now you have to calculate for minus 38 degrees. Then you can plot. Okay. Substitute values for minus 38 degrees 49. Then show me the plot. Students, in this experiment, if you finish first part, then only you can do second part. "49, what happened? "49, CS 11, 49. Share your screen. Calculate RT value for minus 38 degrees Celsius and show me the plot.
So, so
Students, is my voice audible?
Yes, sir.
Sorry, students, here I'm facing power issues, so Wi-Fi is fluctuating. Okay. Okay, 49, very good. Stop sharing. CSE 13, roll number 3.
Yes, sir.
Share your screen.
Sir, these are the values.
Okay, show me your plot. Right. Close this plot. Share your screen now. 3. What is alpha? Name of the alpha.
Alpha 0.00385.
That is the value of alpha. What is alpha?
Temperature coefficient.
Theory.
sir.
Right. And what is the meaning of temperature range? What is the meaning of temperature?
The selected material can take up to this temperature, sir, in between this temperature.
Not selected material, our device RTD. We are doing experiment on RTD, right? So our
Yes, sir.
RTD we can use within this range, -200 to 850. Okay,
Okay. sir.
right. Stop sharing. CSC 13, roll number 6. CSC 13, roll number 6. Share your screen. In Telangana, helped me friend 30. Right. CSC 13.8.
Yes, sir.
Yeah, 37, you can switch on your mic and you can ask your doubt. I didn't understand your message. CSC 737, you can switch on your mic. What is x-axis, Mr. Vishwanath? What is x-axis parameter and what is y-axis parameter? Sai Vital?
Yes, sir.
So, show me your plot. Right. What is y-axis? What is x-axis on your graph?
X temperature and Y resistance, sir.
Pardon?
X temperature and
X.
Y temperature, sir.
X-axis is temperature, y-axis is resistance.
Yes.
Okay.
Yes, sir.
And you have calculated value for 3 temperatures. What are those 3 temperatures? On graph you can see, right?
Sir, x axis 649, sir. And another one is 757, sir.
Right. Last one.
And another one is 775, sir.
Yeah, 775 degrees Celsius. Okay.
Yes, sir.
Stop sharing. Now, students, I hope all of you completed first part of the experiment. Now, I will show you how to do second part of the experiment. And immediately after selecting the bear, you will get time constant as 1.17 seconds. So time constant is the time delay between the response, time delay between the input and output. Students, after selecting bare material platinum, and you have to select with the sheet and observe the figure how it is changing. After selecting the bare material, only material is appearing on the left side. And after selecting the sheet, you will get a outer surface of the RTD. So this dotted line is called as with the sheet. Sheet. And material for this sheet we are selecting. And thickness we can select. When you are selecting or clicking on the thickness, you will get time constant again. So what is the time constant? Time difference between the giving input and accepting input and producing output. That is the delay in between the accepting the input and producing the output. The time delay between these two is called as time constant. And again, Dharma. If you are selecting Dharma, see the figure. That is called Dharma. After this second part, I will show you what is Dharma also through a video. So for Dharma, again, we have to select the material. There is no condition these two materials will be same. We can use different materials. And again, I am selecting thickness and filling material. See, depending on filling material, again, time constant is varying. So like that, if you change the thickness, if you change the material for with sheet and Dharma, and if you change the material for filling, time constant will vary. That we have to observe now. And after selecting MgO powder as a filling material, you have to plot. And you will get 3 graphs. Now we will understand these 3 graphs clearly. So this is the way you have to do experiment, students. I am giving you 2 minutes time to this second part, and randomly I will call the numbers.
So what should we do in graph?
Yes.
What should we do in graph?
We won't do anything on graph, just we will observe the 3 lines. 3 lines represents bare response and with sheath response and thermal response. With those 3 lines, we have to understand the working of the RT. And take pictures of your experiment, and after the tomorrow or today, I will create a link to upload your responses for the first experiment in Moodle. CSC 146. CSC 146.
Yes, sir.
Share your screen. Right. What is the blue color line?
Bare, sir.
Green color?
Which sheet?
Red color?
Thermowell.
So what did you understand by observing these 3 lines? And what is the yellow line?
Input, sir.
Input, right. So what did you understand? So what is the x-axis here? Time. What is the y-axis? Temperature. So bare line is reaching input with the short time period, and if you use with the sheet, the RTD is taking a little bit more time to reach the input, and if you are using thermowell, and it is taking more time to show the input as output. If you use only bare platinum wire, immediately it will give response. But if you protect it with that bare platinum wire with sheet, it will give output, but it will take some time. That is called time constant. And if you protect with the sheet RTD with the thermowell, again it will give response with more time. Okay, 46.
Okay, sir.
Yeah, stop sharing. Roll number 45, CSE 1.
Yes, sir.
Share your screen.
Sir.
Right. What is the difference between these three lines?
The output will be given, the input, the output will be bit late for the thermowell, then compared
Right.
to with sheet, and then compared to bare platinum wire.
Right. So which is best to get output? Bare one or with the sheet or thermowell?
Bare one.
So by observing these responses, we can conclude that bare is giving output with the shorter time periods, but I will show you a video what is the use of sheet and thermowell. Stop sharing your participant.
Sir, can we get these lines in a negative also, sir?
Yes.
In negative also we can get these lines, sir. Negative axis.
Your voice is little bit noisy, student. I'm unable to understand. Can you repeat once again? Is the response? Yeah, right.
Is my graph correct, sir, or wrong? Because I'm getting in negative axis.
No. So in your website, for your link, software has conducted experiment for the negative temperature. On y-axis, you can observe. So what is the final value for on y-axis? It is in between minus 150 to minus 175. That is temperature.
Yes, sir.
So if you want to measure minus 160 degrees Celsius, let us say minus 160 degrees Celsius, you can observe here. Blue color line is reaching the step input with the shorter time period. Did you observe that? Have you observed
Yes,
that?
sir. Yes, sir. Yes, sir.
Okay. And green color line
Bit more
is
time.
reaching. So whatever may be the temperature, positive or negative, the point here what we have to understand, bare RTD is giving response in shorter time periods. With the sheath, it is taking little bit more time than the bare. And if you are using thermowell, it will give response, but it will take little bit more time than the which. That you have to understand. And already in the first part, we have seen the range of the RTD,
Yes,
minus
sir.
200 degrees Celsius to plus
850.
850 degrees Celsius or 890. So that is the range. So in these two, you can do or you can use RTD for your link. Software has conducted experiment for the minus degrees Celsius.
Yes, sir. Thank you.
Temperatures. Right.
Excuse me, sir.
Yes.
Sir, you told we have to submit something, right? Like you'll put something in the module. Could you please repeat that again?
You take the pictures because this is a website, no need of login or sign in, right? So
Yes, sir.
for your website, for your laptop, your mobile, take pictures, and today or tomorrow I will create a link in Moodle to upload those photos. That will be the proof for you that you have completed first experiment.
Okay, sir. So no need of writing anything in the book or something, right? Only the
That I
screenshots
will
are
tell
enough.
you. So that I
Okay,
will
sir.
tell you. So this is first experiment. So I have to coordinate with the other faculty also. If necessary, you have to maintain a note.
Okay, sir. Thank you, sir.
Right. But that I will tell you. What you have to write in that observation or record, I will tell you. So here, students, this is a video which will give details about the use of the thermowell. And these are the RTDs. So in this way, we have to insert RTD. So this is our RTD. And this is called thermowell. We have to insert RTD in thermowell to protect from the chemicals or to protect from the damage of the RTD because of the some solids which are flowing in the fluid. So that is the use of thermowell. And students, RTD we have analyzed in two parts. First part is static characteristics and second part is dynamic characteristics. And analyzing dynamic characteristics means we are using with sheath and with thermowell and how its response will be dragged. Okay, that is called dynamic characteristics. And static characteristics, Whether that is producing a linear output or not, that is first part. So we have taken 3 temperatures and we have calculated RT for 3 values and we have plotted graph, and the graph we got as a linear response. That is first part. Now, if you are using RTD to estimate high temperatures, always if you want to measure its resistance, that is not advisable. Okay, so only depending on resistance, we should not use RTD. We have to connect that RTD to an electrical circuit. So if you connect RTD in an electrical circuit directly, this temperature will change the resistance of the RTD, and RTD will get change in its resistance, and resistance variation will produce different outputs in that electrical circuit. I will show you another video how RTD is connected to an electrical circuit and how the temperature will be estimated. That other video we have, I will show you the video.
Resistance to the flow of electricity also increases.
Students, is audio coming? Students?
Yes, sir.
So are you able to hear this audio?
Parts of RTD.
Is audio coming for this video, students?
Yes, sir. Yes, sir. Coming.
Sensing element or RTD element. The sensing element is the actual temperature sensing unit which is located at the tip of the temperature sensor on the end that is exposed to the process temperature. The sensing element, which is constructed of metals like platinum, nickel, copper or tungsten, respond to the process temperature by generating a measurable resistance. Lead wires. Lead wires are attached to the sensing element and then pass through the sensor sheath. Lead wires connect the sensing element either directly to the DCS or to a temperature transmitter connected to a DCS. Sensor sheath. The sensor sheath is constructed of metal and holds most of the component parts of the temperature sensor. The sensor packing, typically magnesium oxide, surrounds the sensing element and is contained within the sensor sheath. The sensor packing decreases the impact of process vibration on the sensing element and thus ensures a more accurate measurement. Threaded adapter. The threaded adapter is welded over the rear housing of the sensor sheath. One end of the threaded adapter threads into a thermo well or directly into the process piping. The other end is typically threaded into a temperature transmitter. Working of RTD. Suppose we want to monitor the temperature of an oven. To do this work, the probe of an RTD is inserted into the oven. Due to the temperature of the oven, the resistance of the sensing element of the RTD varies correspondingly. The RTD gives output of resistance in ohms, but that is not a standard signal that can be transmitted into the control room. So we have to convert that change in resistance to a change in voltage, and this can be done using Wheatstone bridge. These Wheatstone bridge circuits are built into the transmitter, PLC, DCS or PID controller. RTD may be located hundreds of feet away.
RTD has leads. If you connect those 2 leads to an electrical circuit, so now RTD will become a resistor. but that resistor is placed in high temperature. So whenever we have fluctuations in temperature, depending on that variation in temperature, RTD resistance will vary. So whenever we will get variation in resistance, that will be shown on voltmeter to this circuit.
Away from the bridge circuit. Two types of Wheatstone bridge circuit configurations are mainly used. One is null balanced bridge and the other is deflection bridge. In null balanced bridge, the resistors R1 and R2 are known and R3 is an adjustable resistor. The resistor R3 is initially adjusted in order to obtain 0 volt in the voltmeter. In this condition, the bridge is said to be null balanced. This would be the zero or set point on the RTD temperature output. As the RTD is inserted into the oven, the RTD temperature increases and correspondingly the voltage indicated by the voltmeter also increases. In deflection bridge, all three resistors are fixed and not adjusted and the output voltage varies corresponding to the temperature of RTD.
So you can listen once again.
Resistance to a change in voltage, and this can be done using Wheatstone
Wheatstone
bridge.
bridge is a electrical circuit, one type of electrical circuit, and here we have 4 resistors. This is also one type of resistor. It is called potentiometer, and these two are fixed resistors. And this is a battery power supply, and here we have voltmeter connection.
These Wheatstone bridge circuits are built into the transmitter, PLC, DCS or PID controller. RTD may be located hundreds of feet away from the bridge circuit. Two types of Wheatstone bridge circuit configurations are mainly used. One is null balanced bridge and the other is deflection bridge. In null balanced bridge, the resistors R1 and R2 are known and R3 is an adjustable resistor. The resistor R3 is initially adjusted in order to obtain 0 volt in the voltmeter. In this condition, the bridge is said to be null balanced. This would be the zero or set point on the RTD temperature output. As the RTD is inserted into the oven, the RTD temperature increases and correspondingly the voltage indicated by the voltmeter also increases. In deflection bridge, all three resistors are fixed and not adjusted and the output voltage varies corresponding to the temperature of RTD. If a voltage transducer replaces the voltmeter, a 40 to 20 milliampere signal, which is proportional to the temperature range, can be generated. By this, we come to the end of this video.
So this is our experiment, students, today, and we will meet in next class. If you have any doubts, you can ask. I will continue this session for 5 minutes. If you have doubts, you can ask.
No.
Yes.